welcome back to another video. This time I'm going to be talking about calling conventions of calling functions in assembly, but kind of how you might be able to call other languages such as C functions. So we'll just do a quick recap on what we're doing. So at the moment we're looking at x86 assembly, and the reason is because I'm writing in a little operating system. In fact, what we could do is just run it. So yeah, we've got a little operating system, it's got some things. There's a video about how it works in one of the previous videos in my stream. This version that you can see here is has a few more features than that video, but I'll do an update on what I've changed in the meantime at some point. So last episode we talked about x86 assembly, the different modes. So we've got real mode 16-bit, we've got protected mode, which is 32-bit, and we got long mode, which is 64-bit. And these bits are kind of talking about how many bits there are in a word, which a word is kind of the kind of size of an argument to a function, and well, it's kind of the size of what's on the bus, which the bus, and I'm just saying more and more jargon. Basically it's the size of an argument to a function, and if you've got something that's bigger than that size, you need to have some sort of structure with a pointer to that, when the pointer size happens to be whatever it is. So in our case 32-bit. So we're not using 64-bit, so let's get rid of that. And 16-bit is only really used for the boot process, which will be talked about in an upcoming video. So in assembly we have registers, we don't really have variables like we have in higher level languages. So we've got a few different registers. All these ones here, SP, EIP. There's a few others, but these are the ones I'll probably be talking about mainly in this video. To kind of recap, these first four, these first four kind of used for whatever you want, but in kind of traditional terms, the A1 was used for an accumulator, the B1 was used for like a base of an array type thing, C is a counter, and D is your like data, and ESI is your source string, EDI is your destination string, EBP is your base pointer of like a stack frame, which we'll talk about soon, and ESP is your stack pointer, which is where you push and pop things from the stack, and EIP is the current instruction pointer. So we'll just talk quickly about the stack. We'll make a little stack diagram like this, and make it, I don't know, that big. So our stack pointer, maybe we'll start it at that. In reality, we'll start it at some large value. That's not that large, but that's alright. And where the current point is, so say this is ESP, and EBP is normally the same as ESP when we start, because it's the base of a stack frame. And when we push stuff, what happens in reality is the stack is reversed. So when you push stuff, you subtract off the stack pointer, and basically it grows downwards into memory, but in terms of visualization I'll show it growing up. Basically the operations you can have on a stack, you can have a push and a pop, and what a push will do is, I might just separate it like that. In fact, let's ignore the EVP for now. When you push a variable, say we want to do a push 1, so that would look like that in assembly. And then we'll just push 1, and that would move the stack pointer like so. And when we want to pop something, we might pop into a variable register. So currently EAX is 0, and when we pop, what we do is we basically move the stack pointer back, and whatever the value was there, we will set to be in whatever register that we're looking at doing. So let's push and pop. Next kind of thing that we want to talk about is a stack frame. So here's where a very basic stack frame without like any arguments or anything to a function. So say you had something like a function called foo, and you wanted to just call bar, and then you would return. And all bar did was return. Maybe it did a nothing to start with. In fact, we'll change that to just do a hold. So this is pretty basic. Doesn't really have support for calling other languages, but it gives us two things that we'll look at. So we've got the call and the ret instructions. Now what the call will do is it basically will modify a few different things. So we've got EIP. So say we are at this point here, we've just somehow got into weird filters. So we'll call it foo plus 0. The plus 0 is normally showing how many bytes pass this label. In my case, I can't be bothered doing the bytes because this call instruction might not be 1 byte long, it might be several, but I'll say this point is foo plus 0, this point is foo plus 1, and this is foo plus 3, this is bar plus 0, and that's bar plus 1. So, right, we kind of have we're only looking at stack pointer and EIP here. These are the two things that will change. So when we call bar, what we're going to do is we're going to push the next instruction onto the stack, and so that will change ESB, and we will also change the EIP to be basically the entry point of the function we're in. So at that point, we're at this point here. Not doesn't do anything, so we will just go over, and now we're at ret. What ret does is it pops whatever value is in the stack into EIP. So we're going to go foo plus 2, and the pop will basically remove that value and move this back to the start. And you'll see here we are now at this point. So that basically successfully called a function and returned and knew where to go afterwards. So that's pretty cool. But the problem is that most languages, say C and other languages, don't really just call functions like that. You need to have more of a frame. So to do that, you would have a base pointer as well. Now, when you do this, so I have a macro in my language, which cdecl, which is basically calling a C function, which I use reasonably extensively. So basically all my assembly functions that are used in libraries, I treat them as C functions. And you can have multiple arguments, and it will just do that. How this would kind of get set in assembly land, well, we can actually see if we go to a source that includes cdecl. Can we let's just do that. So it does like a bunch of things, but do that, and then we'll do that, and then it'll call and do that. So those lines there are basically what that does. It also does some like stack alignment stuff, which you can kind of see with these like ands, and add some certain size, and that's just kind of aligning the stack to be at a 16-byte boundary, which is part of the C calling convention. So the C calling convention, otherwise known as cdecl. But as you can see, this takes up quite a few lines, so I tend to just have a macro around it, so that does that. But we might just keep it there just to kind of show what it is. So yeah, maybe instead of having that, we'll just kind of show that wasn't what I wanted. That was cool. And say bar wanted to get, say, the third argument. So what we would do is we would minus that, and we want to get the third argument, which should be 3. We would do like 3 times 4. The random keys there, I've got a strange keyboard, and depending if I have a key down or not, it'll do different things, but I was trying to do numbers the whole time, but that's how it goes. So this minus 8 is, will get explained shortly. We'll also start a function with this and end it with this. And maybe we will store that to EBX, and I'll do this here and this here. So I'm kind of just showing a bunch of things, and maybe, well, actually maybe the first argument will be there, and the second argument will be in B, and the third will be in C. And that's all it does. Doesn't do anything with it, so we'll just have that. Now, the EBX, you'll see I've pushed that onto the stack, and that is because of these arguments, of these registers here. EAX, ECX, and EDX are known as called saved, and the rest are called saved. That basically means that if, say, foo wanted to reuse ECX for some reason, not there, before this point, it would pop it, because it, for some reason, needs ECX. It doesn't actually, but if it did, you would have to save it onto the stack. And likewise in bar, well, oppositely in bar, because EBX isn't in this list, it means it's called eSaved, which means bar, which is called E, needs to save it, because foo might be using it and expects bar not to be touching it. For now, we will kind of ignore that, because we're going to step through, and we're just going to have EAX, and we'll take away that and leave it just with this. In addition to these, EAX is kind of special because it is the return value, which could either be a primitive like int, or it could be a pointer to a struct, if it's a bigger than an int value that needs returning. And I should also note that on 64-bit mode, this isn't correct. There's a bunch more registers, like 1 to 8, I think it is, and you would store, instead of pushing, function calls push args to stack, but in 64-bit args go in regs. But we're not doing 64-bit, so who cares about that? So we see here we're pushing args to stack in reverse order. So the first arg is actually 1, and then 2 is the second, and 3 is the third. And here we're going to get the first arg. So let's step through this whole crazy thing. So the first thing we do is push EBP. So EBP currently is 1000. EBP stays where it is, but because we pushed, we're now there. Now we're going to move EBP to be whatever ESP is. So I probably could have done this in one step, but it was 2 instructions. And at this point, I'm making life hard by doing this. We're going to push a bunch of values. So we're going to push 3, then we're going to push 2, then we're going to push 1, and I need to do that thing, and there isn't a 0. In fact, that's not what I wanted. Just making my stack a bit bigger. Let's get this back in screen. So we've done all those pushes, and then we're going to call. So we remember from last time, when we call, we're going to, this is, I haven't updated that, so 0, 1, 2, 3, 4, 5, 6. So we want this to be 5. We're on the call instruction, but we're going to, sorry, I'll try and might delete this stuff here. I bumped the font up because it was a bit small in the last video. So we're going to push the next value, the next instruction, onto the stack. So ESP is going to go there. And then we're going to also, at the same time, set this to be bar plus 0. So this is similar to what we had in the last one. And now we're at this enter instruction. So what enter does, in fact, let's say that this bar has a variable that we want to look at. So it's going to have a var that's like just an int, and we'll maybe set it to 0, but not actually do anything with it. And what we do here is we're going to basically allocate space for that var, and we're going to exp. Oh, yeah, that should be a B, yeah. And I think it'll just be that. We'll find out in a sec, but maybe we'll set this to 42, just so we know it's a value. Right, so at this point we're at the enter instruction. What enter does is it pushes EBP. So we're going to do a push, and we're going to set EBP to be whatever it is. So that is like 104. So this point here, you can just write that there. And then it will basically add, or subtract in reality, but because we're kind of showing it going down, we might just make a few more frames. We're going to basically add 4 to this, and then we're also going to set EBP, EBP to be there. So now EBP is no longer there. And you'll see kind of what's happened here is, and on purpose, there is nothing at this point here. But you'll see here what we have is kind of a stack frame. So this is a frame of values that will, this point here is like all the variables we have. This here is the pointer to the last stack frame. And this is the return address, and these are the function arguments. And then this is just a pointer to the previous stack frame, just in, because we had to align stuff, which we don't really do here, but yeah, that kind of is how it all works. Yes. So now at this point, and we have done the enter instruction. So now at this point we want to, yeah, I think this should have been a 4. We want to set our variable to 42, so that is basically that. So you can kind of see here, these are all our variables that we're using. These we don't want to touch at all, and these are our function parameters. So at this point we want to go to the next instruction, and now we want to set EAX to be whatever. Oh yes, yeah. So EBP is actually here. So the enter will basically set EBP to be not there actually. Here. It will set EBP to be the top of the frame, so that being the frame, and then the arguments are between EBP and ESP basically. And so you'll see here that ESP is used here and EBP is used there. So now we want to get the first argument out, so we basically skip 4, 8, and then we get the first one, so that's going to be 1. So we're going to set EAX to be 1, which is what we expected, because up here our first argument in reverse order was 1. At this point here, we want to do this leave instruction. So leave, if we remember what that did, we're going to pop EBP. Oh no, we're I think it's that. Yeah. Live coding. Yeah, that's why that's like that. Yeah. So what we're going to do is we're going to pop EBP. So that's going to be that, and that's going to be there. So EBP is going to be there. This should. I might have got this wrong, but the general gist is the leave is going to basically get it. So yeah, I think basically the leave and the rec are going to get this guy here and set EIP to be there, and at the end of it ESP and EBP are going to be at that point there. And we're going to be back up here doing this thing, which is, oh yeah, we can step through that. Yeah, I've just remembered how it works. So we're going to pop EBP. So that's the leave instruction done. That's basically all it does. It pops EBP, and so ESP will go there, and this is actually still just bar something. 1, 2, 3, 4, 8, 0, 1, 2, 3, 4. Yeah. So now we're at the ret. Yeah, this is still not quite right. Yeah. I don't know, live demos. I have read all this stuff before, but ESP should really be here. So the leave knew to skip over these variables. I should have done an example without the variables to start with, but I got away from myself. Yeah, so at this point here, we're now at the ret, and so we'll get this 3 plus 6, so we'll pop it into EIP, and then we will be up to this point, at which point we move ESP to be whatever EBP is. You see what's happening now. And then we will pop EBP, which will be this 100 value, so 1000, sorry. Basically, both EBP and ESP will become that in one, because popping will reduce ESP, and EBP will just get set to whatever the 1000 is. At which point, we're back to where we started, with a bunch of stuff in the stack, but they will just get overridden at another point. And then we hold. So that's kind of cool. So yeah, that's basically how the cdecl convention works in a nutshell. I got something wrong with the ordering of the parameters and the return code. I think it's would have been something like this, and what's this? 8, 2, 3. Yeah, I think it would have been something like this, and we'll just call that X because I can't be bothered with math. I think it would have been something like that, and then when we pop EBP, we basically set that to be there, and then when we pop again, we're going to get the EIP like that. But the documentation will tell you how all that works. But yeah, that's basically that. We don't really need that temp file anymore, so goodbye. And yeah, thanks for watching so far. This video was a bit longer, but it had a bit more to cover. There's a bunch of stuff, and I'll be putting out another video at some point in the future, and hopefully you'll come back to watch that. If you're enjoying this, let me know in a comment or something like that, and I hope you have a good day, and look forward to talking into a video at some point in the future. So yeah.